Hello everyone, I am Bhuvan. I am pursuing BTech in Electronics and Communication Engineering. Today I am going to present my embedded system internship project titled EV ADAS Dashboard. This project was developed as a part of my internship where I worked on building a real-time electronic vehicle monitoring system which was integrated with Advanced Driver Assistance System also known as ADAS. In this presentation, I'll first give you a brief overview of the internship, then explain the technologies I learned, followed by the design, implementation and the working of the project. Now let's begin with a brief overview of the internship. This internship was conducted for a duration of 14 days in the domain of automotive embedded systems. During this internship, I learned fundamentals of ARM Cortex-M architecture and also worked with STM32F103C8T6 Blue Pill microcontroller. I also developed firmware using embedded C and used STM32HAL libraries which made the programming much easier. As a part of the training, I also configured the important peripherals such as GPIO, ADC, timers, UART, and interrupts, which were essential in embedded system development. Finally, all the process data was displayed on a Python based real time dashboard, completing the project. Before moving to the actual internship project, I'll give a brief introduction to ARM. ARM stands for Advanced RISC Machine. It is one of the most widely used processor architecture in the embedded systems today. ARM follows RISC or Reduced Instruction Set Computer Architecture. This means that it uses simple set of instructions. Because of this architecture, ARM processors provide high performance and also low power consumption, making them ideal for embedded applications. Today, ARM processors are used in wide range of devices such as microcontrollers, IoT devices, robotics, and automotive systems, where both performance and power efficiency is important. Now we know what ARM is. Let's look at different processor families available under ARM. So, ARM processor families are mainly divided into three types. The first one is Cortex A, which is designed for application processors. These are commonly used in smartphones, tablets, computers, and high performance requiring applications. Next is Cortex M, which is used for embedded systems and microcontrollers. It offers low power consumption while providing efficient performance. This project uses STM32 Blue Pill. It belongs to this Cortex M family. The third is Cortex R, which is designed for real time systems. These processors are commonly used in automotive features and industrial applications where real time response is needed. Now we had a look at different ARM processors. Let's understand why ARM is used. In the previous slide, we looked at different ARM processor families. Now let's understand why ARM processors are widely used in embedded systems. One of the biggest advantage of ARM processor is their fast instruction execution, which allows tasks to be performed efficiently. Another important advantage is the low power consumption. ARM processors also provide high efficiency, which means they can deliver good performance while consuming less power with few hardware resources. And also, it makes them very reliable for such real time applications. Now we have understood ARM. Let's move on to the microcontroller used to implement this project. So, the controller which is used in the project is STM32F103C8T6, commonly known as Blue Pill Development Board. So, this microcontroller is built around the 32-bit ARM Cortex M3 processor architecture, which uses the maximum clock speed of 72 MHz. It provides 64 kilobytes of flash memory, which is used to store the program, and 20 kilobytes of SRAM, which is used for the program execution. The controller operates in 3.3 volts and provides wide range of built-in peripherals. These peripherals include GPIO for digital input output, ADC for reading analog signals, UART for communication, timers for timing operations, and also support communication interface such as SPI and I2C. Because of the performance and low power consumption, rich peripheral support of the STM32 Blue Pill is an excellent choice for such real-time embedded applications like this project. Now that we have seen the hardware platform, let's look at the important concepts that I learned during this internship before implementation of the project. As you can see, this is the STM32 board. There are multiple pins which can be used for interacting with the board here. Now let's look at the concepts that I learned during this internship. So during this internship, I learned concepts from both embedded systems and automotive systems. On the embedded system side, I gained practical knowledge in the embedded C program concepts, ARM Cortex architecture, STM32 HL libraries, interrupts handling, peripheral programming, and UART communication. Along with this, I also learned important automotive concepts such as electric vehicle basics, advanced driver assistance system, also known as ADAS, real time monitoring, real time data communication, and fault detection and alarm management. Instead of studying these concepts individually, the internship focused on integrating them into a complete one application. Using all these concepts that I learned here, I developed this final project, which is the real time EV ADAS dashboard. Now that I have covered the concepts learned during the internship, let's understand why this project was developed. So, as we know, modern electrical vehicle generates large amount of real-time data from different sensors. So, monitoring this information manually is difficult and also difficult to detect safety-related events. So, for this, we developed a system that can monitor the parameters in real time, detect the nearby obstacles to protect the driver and others, generate ADAS safety alerts, and display the live vehicle information on a beautifully built dashboard. So this project objective was to develop an EV parameter monitor in real time. It should be able to detect the it should be able to detect the nearby obstacles, should be able to generate the safety alerts, display the live information, basically improving the driver's awareness. So this is basically the data flow, how the data flows from sensors to the controller and then to the different parameters set, finally to the ADAS decision making device, and then to the dashboard where the driver can view the details and view the real time data. So this slide consists of the system architecture. You can see first of all the data gets collected from various parameters such as acceleration, brake, temperature, and SOC, which is a state of charge of battery. Next, these data is transferred to the blue pill STM32 board where the processing happens. The process data is then communicated to the dashboard through this UART protocol, which transmits about 1,15,200 bits per second. The final data is visible on the Python dashboard where we can see the speedometer, SOC bar, which is the state of charge bar, and also get a ADAS bird eye view. Now let's have a look at the hardware components used in this project. So this project consists of STM32F103CA-T6 blue pill, which is the main microcontroller used. It performs all the sensor processing, EV calculations, and also determining the logic for the different operations. To detect the nearby obstacles, there are three HCSR04 ultrasonic sensors to detect the front, left, and right of sides of the vehicle using forward collision warning and blind spot detection. We have also used potentiometers for simulation of acceleration, brake, battery, state of charge, and also motor temperature simulations. We have also included 4 LEDs which will indicate the collision warning, blind spot detection, and show the fault status. Finally, the UART interface is used for transferring all the processed vehicle data from STM32 to the Python dashboard for the real-time monitoring. Now we have covered the hardware. Let's move on to the software tools used in the project. So, along with hardware, several software tools are used for the development of the project. The first tool is the STM32 Cube IDE, which was used to write, compile, and debug the code. Next, we are using PixSimLab. So, PixSimLab is a hardware simulation environment. Since physical hardware is not available during the development of this project, we are using PixSimLab for simulation purposes. Next, we are using Python to develop the real-time monitoring dashboard. We have used library like matplotlib where the data is received and displayed graphically. Next, for sending the data from this STM32 to the Python dashboard, we are using VSPE, which is a virtual serial port emulator. This basically transfers the data from STM32 board to the Python dashboard through UART protocol. Now that we have seen the software environment, let's look at the STM32 peripherals and how they are configured for this project. This slide consists of the configuration of the major STM32 peripherals used for this project. Starting with timer 1, it is configured to generate 10 millisecond EV control ticks. This timer ensures that the control logic executes periodically at fixed intervals. Next, timer 2. So, timer 2. It is configured for capturing the ultrasonic sensor echo, which is used for calculating the distance of the object. Timer 3 is used to update the sensor values every 100 milliseconds, ensuring that the fresh data is available continuously. The ADC channels PA0 to PA2 are used for reading the accelerometer position, brake position, and motor temperature. These values are simulated using a potentiometer for our project, as I'll show you in the further explanations. GPIO pins PB8 to PB11 are configured for the digital output of the control LEDs, which is used for collision indication, blind spot detection, and also fault indication. Finally, USART1 using the pin PA9 is configured for the baud rate of 1,15,200 bits per second for serial communication between the STM32 and the Python dashboard. These peripherals work together, providing the sensing, processing, indication, and the communication throughout the project. Now that the peripherals are configured, let's see how the sensor values are acquired using the ADC. This slide explains how the analog sensor data is collected by the STM32. We have these input channels PA0, PA1, PA2, PA3. PA0 is used for accelerator data collection, which ranges from 0 to 100%. PA1 is used for brake, which is again ranging from 0 to 100. PA2 for state of charge of the battery, ranging from 0 to 100%. And then PA3 we have for simulation of the motor temperature, which ranges from 25 to 120 degrees Celsius. All these analog values are converted to digital values using the STM32 12-bit A to D converter. Since the data is 12-bit, the converted data value ranges from 0 to 4095, which provides sufficient resolution for the processing. Now that the sensor data has been acquired, let's see how these values are converted into actual vehicle parameters using the EV Dynamics engine. So the EV Dynamics engine is responsible for simulating the behavior of the electrical vehicle using the input values acquired through the ADC. Based on the accelerator, the brake position, and the controller, calculates the motor torque, which ranges from 0 to 250 Newton meter. It also calculates the vehicle speed, which ranges from 0 to 200 km per hour. The state of charge is also calculated and constantly decreasing, like in real world. We have used a 20 kilowatt hour battery model for this. The driving range is calculated based on the SOC and the efficiency, which is again calculated from the accelerator pedal position. And also we are able to calculate the regen braking, also known as the negative torque, which is generated because of the brake application, and the SOC recovery due to the negative torque generated. Now that we have discussed the EV parameters, let's move on to the ADAS module, where the system monitors the surroundings and detect the potential obstacles. So after calculating the vehicle parameters, the next important module is the Advanced Driver Assistance System, also known as ADAS. This project ADAS is implemented using 3 HCSR04 ultrasonic sensor. As shown in the table, one sensor is placed in front, one at the left and right side. These sensors constantly measure the nearby obstacles or vehicles in our case. Looking at the detection threshold, so FCW warning is generated when the obstacle is, is detected by the front ultrasonic sensor and the distance is less than 50 centimeter. The detection becomes FCW critical when the distance is less than 20 centimeter. In our case, the car is about to hit the obstacle. Next, we have blind spot detection, which has a threshold of less than 30 centimeter and the speed greater than 20 kilometer per hour. The controller also calculates time to collision warning. TTC warning is calculated when the time is less than 3 seconds. And this function further becomes TTC critical when the time is less than 1.5 seconds. It is treated as a critical condition. These safety features help to improve the driver awareness by continuously monitoring the surrounding and providing alerts to the driver. Now that the system can detect unsafe situations, the next step is to manage these conditions using fault management system. So the controller continuously monitors the important operation parameter throughout the vehicle operation. The first fault condition is the motor over temperature. This occurs when the temperature of the motor rises more than 90 degrees Celsius. Next, we have low battery state of charge, and the battery percentage decreases to less than 2%. Next, we have collision fault, where the obstacle distance is less than 20 centimeter. Next, we have sensor timeout. Sensor timeout is triggered when ultrasonic sensor is failed to work and is not producing any data. Next, we have UART timeout, which occurs because of the UART communication timeout or communication loss. Once the fault is detected, the system assigns the appropriate alarm priority. So none indicates normal operation where no abnormal condition exists. Next is advisory. Advisory is used when low priority events like blind spot detection or overspeed conditions are occurred. Next, we have warning, which indicates potential hazard such as obstacle within the warning range or time to collision below 3 seconds. Next, we have critical alarm, which triggers when the common collision distance is below 20 centimeter or the time to collision is less than 1.5 seconds. This ensures that the driver receives the appropriate warning based on the severity of the situation. Now that we have seen how faults are managed, let's understand how the controller itself manages different operation modes using the finite state machines. To make the software more organized and reliable, this project uses a finite state machine, commonly known as FSM. Instead of executing every function continuously, the controller operates through the predefined states. So looking at the table, we can see that the system starts in park mode when the power is turned on initially. Once the accelerator is pressed, the controller moves to ready state. This indicates that the system is initialized and ready for operation. As the accelerator input increases beyond the defined threshold, the controller enters driving state, where EV dynamics module continuously calculates the speed, torque, battery charge, and other vehicle parameters. Next, when brake is applied, the controller switches to regen state. During this state, regenerative braking is simulated to recover the energy produced in braking and transmitted that energy into the battery to recharge it efficiently. If a critical fault occurs such as motor overheating or low battery or collision risk, the controller immediately transitions into fault state. In this state, normal operation is stopped until the fault is cleared. Using FSM, it is easy to maintain and makes the system more reliable. Now let's look at the actual transition diagram and see how these states are connected. So as we can see, when the system is turned on, it is in park mode. When the accelerator is greater than 2%, it switches to ready mode. Greater than 5%, it goes to driving mode where the vehicle is actually moving. The brakes are applied, that is about greater than 10%, it switches to regen mode. This regen mode is used for recharging the battery, which converts this braking energy into electrical energy for the battery. When the brakes are less than 5%, it then switches back to driving mode, and this cycle continues until a critical fault occurs. So if there is a critical fault, it switches to fault mode, and the command is reset, and and the car goes to park mode finally. So these are the fault codes for the each independent fault occurring, such as like if the fault is none, the code displayed is 0x00, saying that no abnormal conditions are existing. When we have a fault OT which is over temperature, we get 0x01, which indicates motor temperature warning. Next we have fault SOC, which represented by the code 0x02, which indicates battery is critically low. Next we have fault COL, which is represented by 0x04, which says the collision critical. So all of these fault codes can be viewed on the dashboard, which I'll further show you in that project demonstration. Now let's move on to the real-time monitoring dashboard. So this slide contains the data of the Python-based real-time dashboard, which was developed for this project. The STM32 continuously sends the data through the UART communication protocol. And the Python application will receive all this data and update the dashboard in real time. So in dashboard, we have integrated speedometer, which displays the real-time speed of the vehicle. It ranges from 0 to 200 km per hour. It also displays battery state of charge, which shows battery percentage and estimated range. It also shows a graph, which is a speed history, displays live speed trend over time. Next, we have EV metrics, which shows torque, acceleration, brake, temperature, and fault status. Next, we have ADAS bird eye view, which displays obstacle distance and collision alerts. So this is our dashboard. This is how the dashboard looks. This is the speedometer. This is the state of charge indicator. The speed history, which varies over time continuously. This is the EV metrics, where data such as torque, acceleration, brake, motor temperature, alarms, fault, and signal, everything is displayed. Next, we have ADAS bird eye view, which shows our vehicle. This is the potential obstacle, its distance, and green line indicating we are at a safe distance. We also have time to collision calculation here, which shows the time required for the object front of us based on our speed to collide. So now let's begin with the project demo. So this is the STM32 Cube IDE with the project code was developed. So the main project is the EV dash. Under EV dash we have multiple files. These are the .c files, and these are the header files. So this is the main file, where we have included many header files such as EV control, ultrasonic, ADAS, fault, and UART shell. So many folders were developed for this project in order to keep the code tidy and easy to debug. So let me build this project. I'll right click, go to build project. Here we can observe in the console the project is getting built. It says 0 errors and 0 warning, and also a binary file is created. Now let's execute this code on the Pixim lab. So this is Pixim lab, and this is our STM32 103C8T6 board. First I'll show the spare parts. So you can see these are the potentiometer for simulating the acceleration, brake, SOC, and motor temperature. We have three ultrasonic sensor constantly measuring the front distance, left distance, and right distance. We also have these LEDs here. This red LED will light up based on the threshold parameters set for the front ultrasonic sensor, blue one for the left, similarly green for the right, and this yellow LED is used for general fault. So if this LED lights up, then we know there is some fault. This is just a virtual terminal for displaying the data, which I'll show in the further demonstrations. So first, before changing the parameters here, let's upload our binary file into the board. So I'll go to file, I'll go to load binary, the EV- binary file, click on open. The Pixim lab just reloaded. Okay. Now let's open the virtual terminal and simulate the data. So this is a virtual terminal. You can see it says EV ADAS system ready. It is displaying speed, state of charge, time to collision, blind spot detection, alarm, and faults. So now let's begin with the simulation. First I'll vary these potentiometers and let's observe the change. I'll keep the speed to 100, braking to 0, state of charge to 100, and temperature somewhere in the half. Let's observe the terminal. We can see that the speed is rapidly increasing. The state of charge is decreasing because of the speed increasing, and the torque is also gained for about 147. The motor temperature is about 58. The acceleration is 98 and brake is 0, as we can see. Now I'll put acceleration to 0 and brake to 100% or somewhere in the half. Now we can see that the speed is constantly decreasing. Brake is about 69. The torque is negative, which means that the battery is getting charged. The temperature is same. Acceleration is 0 and brake is about 69. So if I increase the temperature to maximum, we can see that we get a fault code of 1 saying that the motor is overheating, and also the temperature is increased to 120 degrees Celsius. So now let's change the ultrasonic sensor distance and observe the change. So I'll decrease the front ultrasonic sensor distance to about 20. We can see that the red LED is lit up and it detects a fault. So when I reduce this left ultrasonic sensor to about 22, we can see the blue LED is lit up, showing that there is a potential collision happening that could happen from the left side. Similarly, when I decrease this right ultrasonic to about 10, we can see that the green LED is lit up, saying that there is potential collision from the right. So I'll just show them individually. You can see that right is indicating for green color LED, left is for blue color LED. Finally, we have red LED for the front ultrasonic sensor. So finally, let's observe the changes on the Python dashboard. For transmitting the data from this STM32 board to the Python dashboard, we use a virtual serial port emulator. So we can see here the port is set up from COM1 to COM4. This board is set to COM4 and our Python dashboard is set to COM1. Now I'll launch the Python dashboard. So I'll go to command prompt and I'll open the file. Okay. So this is our final Python dashboard. So let's proceed with the simulation. So I'll increase the speed to 100, brake to 0, the state of charge to maximum, and motor temperature somewhere in the half. Now let's observe the change on the dashboard. You can see that the speed is rapidly climbing. So the one thing is I did make some changes in the board in order to speed up the process of the simulation. So the speed is climbing rapidly. Else it will be according to the real time calculations. So we can see that can see the speed history climbing. We can see the torque generated, which is 150 Newton meter. The acceleration is 100%, brake is 0, motor temperature somewhere in the half of 120 degree, so it is about 60 degrees Celsius. Alarm is advisory because we are going over the speed limit. Fault is 0x00 because there is no fault generated, and signal is on because the data is successfully getting transmitted to the dashboard. Now let's simulate braking. I'll keep braking 100% and acceleration 0. You can see that the brake is applied and the vehicle slows down rapidly. You can see the decline in the speed here. You can see that the negative torque is generated because of the deceleration generated. Acceleration is 0, brake is 90%, motor temperature is about 50%, which is similar to the last time. There is no alarm because we are not going over the speed limit and the system is working fine. And also signal is on. Now let's simulate the distance calculations. So I'll change the distance of left to about 56. I'll keep the front to about 66 and right about 26. You can see that these vehicles are appeared much closer to the EV. You can see the front vehicle is about 65, the left is about 55, and the right is about 25. Now I'll speed it up. I'll increase the speed by a little bit. Brake I'll keep 0. You can see because the front vehicle distance is very low, we get a critical alarm. There is a potential collision possibility here, so the system glows red and also displays alarm critical. And also you can see the fault code is generated, which is 0x04, and also time to collision is getting calculated, which is about 0.2 seconds based on the speed and the distance of the object. So if I increase the speed a little bit, decrease the left and right even more. If I decrease the left measuring ultrasonic sensor, you can see that the distance is about 9 cm. The time to collision is about 99. So now the value got updated and we can see blind spot left, collision warning, which is advisory. So similarly for and also this blue LED is lit up. Now I'll go back. Now I'll decrease this right measuring ultrasonic sensor. You can see that the green LED is lit up, showing there is potential collision from the right. Observing from the dashboard, we can see the distance is about 25 centimeters, so there is a blind spot detection warning from the right, and the alarm is advisory. Now let's observe the motor temperature warning on the Python dashboard. I'll increase the motor temperature to maximum. On the dashboard, you can see the motor temperature is about 120 degrees Celsius. And also a fault code is generated. And you can observe that the torque generated is 0 Newton meter, even though the speed applied is not 0. This is happening because, so according to fault code, as the temperature of the motor increases beyond the threshold, the system goes to park. So no torque is generated and also system is not moving forward. So this concludes my dashboard simulation. So this brings me to the end of my presentation. Thank you all for your time. I would like to sincerely thank Emertxe for giving me this opportunity to undertake this internship, and also my mentor Jalakshmi ma'am for guiding me throughout the project. Throughout this internship, I gained practical knowledge of ARM architecture, STM32 microcontroller, embedded C programming, and peripheral interfacing. And also, developing the EV ADAS dashboard helped me to understand how different embedded systems and concepts are integrated to build this real time application. This experience has strengthened my technical knowledge, problem solving skills, and confidence in embedded system development. Thank you once again.